Okay, welcome back to the second video on transition elements. This is exciting stuff indeed. One of the most important things about transition elements is their ability to form complex ions. They do that with ligands. Okay, we've got a few subject-specific terms here. What is a complex ion? Obviously, you can read that definition for yourself. So if we have a transition metal ion, a central metal ion, and then we've got either negatively charged ions or molecules forming dative covalent bonds, coordinate bonds to that central metal ion. The molecules of the negative ions are known as ligands. So, similar definition, what's a ligand? A ligand is a molecule or a negative ion that is able to form a dative covalent bond to a central metal ion. The two definitions are clearly very, very linked. But you must know them. Absolutely must know them. Now, coordination number is the number of dative covalent bonds made to the central metal ion. It's not the number of ligands. That's really, really important. So we've got the number of dative covalent bonds to that central metal ion. And that will become clearer as we go through this next section. Now, copper sulfate. We know that copper sulfate contains aqueous Cu2+ ions. But actually, it's a little bit more interesting than that. Copper 2 sulfate contains what we call the copper hexa-aqua ion. It's a transition metal complex. It's a central metal ion, copper ion. Do you know what? I'm going to change the colour of my pen to make it the right colour. You understand? I've got the copper 2+, and the copper 2+ is going to be surrounded by water molecules. Each water molecule is able to form a dative covalent bond, coordinate bond, to this central metal ion. So, when we do this, what we actually find is that our copper is going to be surrounded by six water molecules. I'm going to draw 4 of them flat on the board going to the points of the compass. It's important that we draw our ligands, our water molecules, so that the oxygen, it's the oxygen that's got the lone pair of electrons. The oxygen is at the end of the dative covalent bond. I've also got a water molecule sticking directly out of the page, and another one going into the page. So there are 6 water molecules, hexa-aqua, surrounding our central copper ion. Now, what happens to that 2+ charge? I draw my complex inside square brackets, and the overall charge goes up in the top right hand corner. So there are 2 ways that we can represent a transition metal complex. We can either draw out a diagram showing where the ligands are as a 3D representation, which I've just done, or we can write it as a simplified formula, H2O6, all in square brackets with the charge on the outside. Colour. This complex is pale blue. As many of you are already aware, this is the part of the syllabus where you have to memorise some colours. Pale blue is the copper hexa-aqua ion. The bond angle. The angle between all of the bonds is 90 degrees. The coordination number I'm not counting the ligands, I'm counting the number of coordinate bonds. 6. This shape. Octahedral. Now, that can seem a little bit confusing, but it's octahedral because what I effectively have when I have my transition metal ion, I have got a square-based pyramid, and then another pyramid, square-based pyramid on the bottom. So it's two square-based pyramids stuck together on the square bit. On the outside surface, there are 8 identical faces, 8 identical triangles. So although there are only 6 ligands, although there are only 6 dative covalent bonds, the name of the shape is octahedral. You've got to be able to draw 3-dimensional representations. This octahedral shape, absolutely central to transition element chemistry. You also need to know the colours, coordination numbers, bond angles. These are the kinds of things that are important to us as chemists. So there is the copper hexaaquat ion. That's the first thing that you need to learn. Oh, what is coordination number? The number of coordinate bonds made to the central metal ion, not the number of ligands. It does tell us, it's pre-warning us of something that's going to come later. Some ligands can make more than one dative covalent bond to the central metal ion. Some can only make one, some can make more than one. We've got some special terms for those things, which we'll come to later. Reactions. Reactions and colours. The first types of reaction that the transition elements do, these are the simplest. If we take some sodium hydroxide solution and add it to different transition element solutions, we will form precipitates. We need to know the formula of the aqueous ion, we need to know the formula of the precipitate, and we need to be able to write ionic equations for the formations of those precipitates. So if I take some Cu2+, now, do I need to write out the full transition metal complex formula? When we're doing precipitation reactions, OCR are very generous to you. They don't make you write out the full formula of the transition metal ion complex. We're allowed to kind of almost slip back to GCSE level. I'm able to represent my copper hexaaquat ion as Cu2+ aqueous in a precipitation reaction. I'm emphasising the point here, in precipitation reactions I can do this. I'm going to react my copper hexaaquat ion, my Cu2+ aqueous, with 2 hydroxide ions. State symbols are crucial to make my copper hydroxide precipitate, which is a solid. I go from a pale blue solution and I form a pale blue precipitate. Remember, the word precipitate in chemistry means you add 2 solutions together and make a solid. When we come to the ion 2, Fe2+ aqueous, we'll react again with 2 hydroxide ions, also aqueous, and that will make ion 2 hydroxide as a solid, as a precipitate. Pale green solution to a dark green precipitate. colours as state precipitate, really crucial. It doesn't matter how much sodium hydroxide I add, I just form this precipitate. So the moment I add a few drops, the precipitate forms. Again, in gallons of sodium hydroxide, I will still just get this precipitate. Now, blue precipitate for copper hydroxide, dark green precipitate for iron hydroxide. Learn those colours. Iron 3 follows the same kind of pattern. So, in iron 3, I'm going to be going from this kind of orangey yellow solution. I'm going to now add 3 lots of hydroxide to make iron 3 hydroxide precipitate, which is an orange-brown precipitate. Manganese when it is in the hexaqua ion is a pale, very pale pink solution, and when we go to the hydroxide, let's just get the right colours, grab my 2 hydroxides, so aqueous, and we're going to end up with a pale brown precipitate of manganese hydroxide. Learn the colours of the solutions, learn the colours of the precipitates. Now all of these diagrams, all of these pictures of the various solutions and precipitates are taken from the OCR sheet that states all of the things that you need to know in terms of colour. So these are really, really important. Make yourself some flashcards or whatever it is that you do, but you must learn these colours. The good thing about copper, iron 2, iron 3 and manganese is that it doesn't matter how much hydroxide you add, the precipitate is insoluble. That is not true for chromium. Initially, when we get our chromium, now this is really interesting one, the chromium 3+ hexaqua ion is a kind of purple colour. When we add our hydroxide, drops of hydroxide, so a small amount of sodium hydroxide, we're going to get a dark green precipitate. So our chromium hydroxide, so chromium hexaqua, we're going to add 3 lots of hydroxide, and we get this dark green precipitate. Now, interestingly, when you add more hydroxide solution, the precipitate redissolves, and what you end up with is this very dark green. Let's try and find a suitable colour. Very dark green chromium. It's not quite the right colour that I was looking for. A very dark green. Transition metal ion complex. The chromium is surrounded by 6 hydroxide ions. Square brackets. The chromium has a 3+ charge in the middle, each hydroxide is a 1 minus, so overall, we end up with the 3 minus ion. And that is going to be aqueous because of the charge. Now we'll look at writing equations for formation of this later on. So we've got precipitation reactions, transition metal ion complexes. Where possible, we're trying to keep equations as simple and straightforward as possible. We could write more complex equations if we wish. I wouldn't. If I was doing the exam, I'd be keeping it always as simple as possible. It doesn't stop there. We now go to look at precipitation reactions of transition metal ions with ammonia. Now the great news is ammonia, when we've got ammonia in solution, it sets up ammonia is NH3 in solution, and ammonia in solution sets up an equilibrium and forms some ammonium ions and some hydroxide ions. And when we put our transition metal ions with ammonia solution, the transition metal ions react with the hydroxide ions. And so the things that we're going to write on this page are exactly the same as what we wrote on the previous page. Iron 2, iron 3, manganese, these three reactions will be exactly the same, bizarrely, as what was on the previous page. So I'll take my iron 2 aqueous, reacted with 2 hydroxides and make 2 hydroxide solids. So although we're reacting our transition metals with ammonia, it's actually the hydroxide ion, not the ammonia, that they're reacting with. Iron 3 will react with 3 hydroxides, making heavy H3 solid, and manganese is going to react with 2 hydroxides to make manganese hydroxide precipitate. You've got all the colours that you need to learn, but they're exactly the same as on the previous page. This is double value to the price of 1. It does not matter whether you take your transition metal ion and react it with ammonia or with a certain hydroxide solution. The first thing is, for many of these transition metals, you get a precipitate. And for iron 2 and iron 3 and manganese, it does not matter how much ammonia you add, the precipitate is insoluble. However, the chromium, just like before, behaves differently. But this time, so too does the copper. The copper ions, the copper hydroxide precipitate, that was insoluble in excess sodium hydroxide, is soluble in excess ammonia. And the chromium 3 hydroxide precipitate, just like before, is soluble in excess ammonia. So what's going on here then? So to begin with, what we're able to do is take our aqueous copper 2+, we're going to react it with 2 hydroxides, aqueous, and we're going to make that copper hydroxide precipitate. Pale blue solution, pale blue precipitate. But that pale blue precipitate of copper hydroxide, when we add more ammonia, that precipitate precipitate will dissolve and will make a dark blue solution. Now, looking at the formula of the solution that you make, it looks really complicated. We have got here a copper surrounded by 6 ligands. We've got 6 coordinate bonds and 6 ligands. We have got 4 ammonias and 2 waters, all inside square brackets. The ammonia and the waters have no charge, but the copper has a 2+ charge, so the 2+ charge of the copper goes in the top right hand corner outside the brackets. That's the formula of the 3D representation of the complex ion that has been formed. You need to know the colour of that solution. You should be able to draw a 3D representation or write out the formula of that complex ion. This is where the, excuse the pun, the complexity of this module increases. So when we're talking about complex ions, like the copper ammonia complex, you have to memorize that formula, you have to memorize the colour, and you have to be able to draw that 3-dimensional representation. Now, what's happened in the formation of that 3-dimensional transition metal complex that we've just drawn out there? We've got a process called ligand substitution happening. That's going to come in the next video. The chromium is going to behave in a similar way. So the chromium we've got our aqueous chromium 3+, we're going to react it with 3 hydroxide ions. That will form our chromium hydroxide precipitate. Purple chromium hexaquion. We've got the dark green precipitate of chromium 3 hydroxide. When we add our chromium 3 hydroxide into excess ammonia, we now get a ligand substitution reaction. The hydroxides come off, just like in the case of the copper, and we end up with chromium. This time, this is an easier one to remember. Chromium is surrounded by 6 ammonias. That's more straightforward, isn't it, than the copper ammonia complex. The nice thing about chromium, although there's loads of colours to remember, is that when chromium is surrounded by ligands, all the ligands are the same. So here we've got chromium surrounded by 6 ammonias. When we added excess hydroxide, the chromium is surrounded by 6 hydroxides. So it doesn't matter what the ligand is, they're always 6 identical ligands. That wasn't true for the copper ammonia complex. The copper ammonia complex is probably the most complicated transition metal complex that you're going to have to memorize. What I need you to do now is make some flashcards or some kind of online revision thing to help you memorize colours of solutions, colours of precipitates, and what happens when you add excess ammonia or excess hydroxide and you get the precipitate redissolving. There's quite a bit to learn there, but learn it you must, because in an exam they could be leading you into the question by talking about the colours of the solutions and the colours of the precipitates, and that has to activate in your brain the formula of the compound that they're talking about. Okay, that's the end of this video.